Section 3.2 is Rolle's theorem. It's not Rolle's. I know phonetics, it doesn't work out for us all the time. It's Rolle's theorem and the mean value theorem. So we're going to start talking about Rolle's theorem first. Rolle's theorem says that suppose that we have a function that's continuous on the interval AB, it's a closed interval. It's differentiable on the open interval AB, and the endpoints are equal. Then there is a number, C, between A and B, where the derivative is 0. So one basic picture you can have of what this is describing with the conditions the way they are. This isn't, of course, the only way this can be drawn. But you have something like, well, I got to get the right tools, like this, where this is my endpoint A, this is my endpoint B. It's continuous, right? Yeah, it's continuous on that interval. It's differentiable, right? No sharp turns, no holes, no jumps, anything like that going on that cause problems with differentiability. And the endpoints match, right? They have the same y value. So the way I've drawn this, hopefully they look like they have the same y value, whatever it is. Here, we'll write it in that way. F of A equals F of B. So what this is saying is that any time that happens, there must be some location between them. It doesn't have to be halfway, by the way, but there needs to be some location between them. There will be, not doesn't need to be, there will be some location between them where your derivative is 0, or you have a horizontal tangent line. Okay, in other words, there's going to be a peak or a valley. That's really what this boils down to because of the way the conditions are set up. At least one. There could be more than one. We could have multiple places where we have derivatives of 0 with these conditions set up. So as we're looking at these, you have seen this before. We saw this with the intermediate value theorem, where we have these conditions, and if these conditions are met, then something else happens. Do you remember that? Happened on exam 1. And so we need to identify what those conditions are. So the first condition is that it's continuous. The second condition is that it's differentiable. And then the third condition is that the endpoints have the same output value. So if we are trying to decide, which we will be in the next couple of examples, whether or not Rolle's theorem applies, it means that all three of those conditions have to work. And then if they don't work, then I don't necessarily have the condition that follows, and I can't use it. So as we see these problems, we want to determine first if Rolle's theorem can be applied. If it can't, the answer is no, and we're done. That's actually the one we want. It's less work. If Rolle's theorem does apply, second thing, we're going to find the values of C where f prime of C is equal to 0. Okay, so this is the first step, determine, and this is the second step. It's a big if, right? If, and my second step is that I find these derivatives equal to 0. We've been finding derivatives equal to 0, section 3.1, so it's not like that's something that you're not familiar with. It's the first part that's new, the conditions. Okay, so what is the first condition that I'm supposed to check? Continuous. Now, we did this before when we did the intermediate value theorem. We need to justify continuous. I think I got it. We need to justify why it's true. Why is this continuous? Yeah, it's parabola. In specific, or more generally rather, it's a polynomial. Anytime we have a polynomial, it's continuous. So it's continuous because you can say it's a parabola, you can say it's a quadratic, or you can say more generally it's a polynomial. I guess my English could look a little bit better because it's a polynomial. Okay, so that's checked. How about the differentiable? That's step 2. Is it differentiable? It is. Why? Somebody said because it's a parabola. Actually, there's no reason it couldn't be. I don't have any sharp turns. You can talk through it like that. But the reality is polynomials are always differentiable, and we actually had a theorem that said that back in chapter 2. So our reasoning for this is actually the same as it was here. It's because it's a polynomial. Polynomials are always differentiable. So we get that for free. The only one that requires any real work out of us is to test the endpoints. So what are my two endpoint values that it gives me? Yep, 0 and 3. So I need to test if f of 0 and f of 3 are the same. So if I plug in 0, what do I get?
0.
It is 0. What if I plug in 3?
0.
It's actually 0 as well. So these two are equal. That's check 3. So what does that mean? Well,
We have to find the derivative.
yeah, this means Rolle's theorem applies. And we have to do, like Alyssa said, I'm really sorry, I have a friend named Alyssa. Alyssa said, we have to find the derivative. So our second step on this then is to find the derivative. What is the derivative of our function? Negative 2x plus 3. Okay? Remember, derivatives tend to be easier in Chapter 3 than they were in Chapter 2, so that's something to look forward to. What are we going to do with the derivative? Set it equal to 0 and solve. So, as we work with this, I now have negative 2x equal to negative 3, and x is equal to 3 halves. Now, probably should check my calculus and my arithmetic as I did that to make sure. Is that between 0 and 3? It is, and it's actually halfway. I told you it's not going to always be halfway, but parabolas are very symmetric, so it kind of makes sense that it's halfway because of the way that parabolas operate. But this is the c value that we were looking for, so the c is in fact equal to 3 halves. Okay, let's try another one. First step is continuous. Okay, so is it continuous? Well, this is a less familiar to us kind of an equation. Do you know what this is an equation of? Like, is there another way to write it that's a little less abstract? Good. It's a cube root of x squared minus 1. So continuous really means, can I plug any value in for x and it be okay?
You can because it's a cube root.
I can because it's in a cube root and because it's squared underneath, actually. Both of those things are helpful. Because as I square it underneath, it will change it to a positive, so even the cube root wouldn't end up mattering. Yeah, this one's continuous. It actually works. All of my x values are totally just fine. Okay, so this is continuous. It checks out. And the reason is because it's a cube root. That's sufficient. If it were a square root, we'd have to be a little bit more careful, make sure that the domain was actually values that made sense, that sort of stuff. So we get that one kind of nice. How about differentiable?
Yes.
So I'd like for you to take a look at the graph on this one. It's a little bit less familiar of an equation, right? It's not a polynomial, it's not a parabola. You can type it in cube root form or in the exponential form, whichever one you like. You do want your interval, your window, to go from negative 8 to 8. If it goes from negative 10 to 10, that's not going to hurt anything. I'm just going to sketch it here. What does the graph look like? It looks like it bounces a little bit, doesn't it? But it doesn't bounce like a parabola bounces, right? Oh, there's a sharp turn right here. Yeah, this is less familiar to us. What do we do about the fact that there's a cube root? Well, some cube roots are just fine. But the fact is that this one's a cube root and it has the x squared. Those two pieces are not playing nicely together for it to be differentiable. They're not friends, exactly. So we do end up with a sharp turn right there. So when you're working with graphs that are less familiar to you, equations that are less familiar to you, a graph can be very helpful. Because this is very easy to justify now, from a graph's perspective, that it's not differentiable. Because there's a sharp turn. So is it differentiable? And the answer is no. And the reason is because at specifically x equals 0, there is a sharp turn. It's different, I mean, it's continuous there, right? There's no problem with continuity. So we did do the right thing on the first one. That wasn't affected, but the differentiability was. Now we don't have to find the derivative. In fact, we don't have to find the next step either, right? We get to stop much quicker on this particular problem. So this one failed right there. So Rolle's theorem.
So if we have 10 problems and 5 of them
Does not apply. Do you really think that 5 of them will not work if you have 10 problems?
I feel like that would be
Probably not. But there might be one that will, right? There might.
But if there was, this would be so fast.
It would be fast. All right, let's try another one. So we've got to do one with trig. All right. You are familiar with this graph. At least you should be. So the graph of sine of x, first thing, continuous. Yes. And the reason is, and we actually saw it back in chapter 2 as well, or maybe even chapter 1, initially for the continuity part of it. It's continuous because it's a sine curve, right? Not because it's a trig curve. Not all trig curves are continuous, but sine curves are. Cosine are as well. How about differentiable? Yeah. And if you think about it from your differentiability perspective, like the graphing that we just did before, everything's nice and smooth, like rolling hills, right, or waves. It's lovely. Yes, you can. Yes, and it's all because of the same thing. It's because it's a sine x curve. Now let's pause for a moment since I mentioned that this is trig. Sine and cosine both do this, right? But if you used any of your other trig functions, they're not continuous everywhere. So while I do have an interval given here, and I'm going to use it in a moment, that interval did not come into play at all for me making those first two statements, right? Because sine and cosine really are continuous everywhere. If I were doing something with cotangent or tangent or secant or cosecant, I need to pay careful attention to the interval's endpoints. Because what I really want to make sure is that I'm not crossing over an asymptote as I'm doing it. Does that make sense? So just because something shows up that has an asymptote doesn't necessarily mean there's a problem. The asymptote's only a problem if it's on the interval we're being asked about. Does that make sense? So you have a calculator, you're welcome to check and look at that. If you know pieces of the graph or how the asymptotes are coming about, like if it's a rational function and clearly it has an asymptote at x equal 1, because the denominator says x minus 1, then you can utilize those facts as you're making those statements about differentiability, or in this case, continuity. All right, so it's continuous, it's differentiable. So what's my step 3? Check the endpoints. So I need to find out what happens at f of 0 and at f of 2 pi. So what is sine of 0? It is 0. And what is sine of 2 pi? 0. So it checks out. Those are all my conditions. Yay, so Rolle's theorem applies. Okay, so that's good news. Rolle's theorem is going to apply. And it's also good news because it's easy to take a derivative of this function. So what's the derivative of sine x? Cosine x. And we're going to take that then and set it equal to 0. I still need to set it equal to 0 based upon my interval where I'm working, right? I'm still working in the interval 0 to 2 pi. So I want to know where's the cosine graph equal to 0 on 0 to 2 pi. Okay, good. So I think you guys are thinking unit circle. That's my guess. But you might be thinking of a graph. Either of those are possible. I'll draw them out for those of you who are like, how did they get that answer so fast? It is pi over 2 and 3 pi over 2. So one way to come to that conclusion is to think about the graph of cosine, which I haven't drawn. We've drawn sine a couple of times. The graph of cosine looks like that. And these locations where it crosses, like whether you scanned it on your calculator, like traced it across, or whether you simply remember the graph, are in fact at pi over 2 and 3 pi over 2. My graph's not great, but hopefully it still suffices to give you the idea. Or you're welcome to think of it from a unit circle perspective. So if you're doing it from the unit circle perspective, we talked about this last time with sine as our curve that we were concerned about. The cosine values on the unit circle are the x coordinates. So right here and right here, I have x coordinates that are 0. And the angle measure to get to here is pi halves, and the angle measure to get to here is 3 pi halves. So that's a unit circle perspective if that's a comfortable place for you to come from. Okay. Again, what doesn't work is just doing inverse cosine in your calculator because it will only give you one value. And oftentimes your interval includes more than one value. Not always, but oftentimes, like this one it did. So I actually end up with 2 c values on this one, right? Here, I now have that c equals pi halves or 3 pi halves. There's 2 c values that fit the description that I'm looking for. C is just the value that's in the description it's looking for up here. There's just saying what C value does it. X is an arbitrary value. It changes, it fluctuates. C is a constant. We're just looking for the constant X value that does what we want it to do, the location where it does that. So if you left it, Alyssa, and it just said X equals, it's okay with me. I don't know what WebAssign will do. It probably will put C equals in for you, and you'll just put the values next to it probably. But it's not something that's worth taking points off for. Does that make sense? But just know that that's how it's probably going to be stated for them.
So if the derivative is sine x, it'll be pi and 2 pi?
And 0 as well. Yeah, and if this derivative had been sine x instead, and we were looking where sine of x is equal to 0, it'd be 0 on the other corners, right? It'd be 0 at the, I'll change my color, here and here instead. So 0 and then pi and then 2 pi and then 3 pi and 4 pi and 5 pi, and it would continue on through whatever interval we're looking at. Yep. Okay?
So like on an exam, would you have to state like why it's continuous? And
Yes. Thank you for asking that. So what I've seen WebAssign do before, and it has changed, it adjusts itself even when we use it from semester to semester sometimes, is it has you justify why, and it'll have like in a multiple choice format sometimes. If you were doing it on a quiz or a test for me, you'd need to say why. So this isn't the only reason why, it's just maybe the simplest one to write down. This works because it's a sine curve, it works because it's a polynomial. But you can also state the reason behind that, which is it's smooth. It's, every x value works. So like when we were talking about this one over here where it's not quite so direct and we were talking about why we knew it was continuous, we know it's continuous because all the x values are actually able to be used. There's no x values that cause issues in the domain. So
We could put all x values in the domain work. And
you could do that, yeah. So you need to be a little bit careful, make sure it's really true as you're working with them. But yeah, it's true. That's what it means, is that by default, when we did it back before and we said, hey, polynomials always work, we said the reason polynomials always work is because there are no domain issues when we talk about polynomials, etc. for sine graphs and so forth. And cube root graphs. This one's actually causing a problem with differentiability, again, because of the x squared. So if this were not x squared and it were just x underneath here, this piece would actually flip back down, and it would be nice and smooth and continuous, and we would have it would be differentiable and it would work. The problem here is because of the x squared, it's taking part of this and it's flipping it back up. All the x negative values are flipping back up. That's what's happening on that graph. Okay, there's one other thing in our title of our section, and it says mean value theorem. The mean value theorem, there's some give and take. It's actually quite similar to Rolle's theorem. Actually, Rolle's theorem is just a special case of the mean value theorem. So the mean value theorem says, suppose it's continuous and it's differentiable. Okay, so that's the same, right? But notice what's not there.
The endpoints.
The endpoints do not have to match for the mean value theorem, okay? But what it talks about instead is the additional sort of piece that's going on. So if it's continuous and it's differentiable, then there will be a c value between a and b where f prime of c equals f of b minus f of a over b minus a.
So slope.
Thank you. I was about to ask that question. You didn't even make me ask it. You're right. This is slope. Did you guys recognize it? It's an equation for slope. So here's visually what it's saying. So if you can imagine taking the graph that we did before, which looks like this, and somehow taking it and like shifting it and putting on an angle. So now, instead of it looking like this, I bet I can do this. It looks like that. This is the picture that you have. So what happened before is that if you connected to the endpoints and they were the same, in fact, I'm going to do that from here. The endpoints were the same, at least they would be if I drew it well. Okay, we're just going to go with it because it's going to mess up if I put that eraser mark in there. And then we take this and we shift it. All we're saying is that the location, oh, actually, let me put one more line in there. There was a derivative that was 0. That's actually what the Rolle's theorem said. And what the mean value theorem says is that I can take all of this and I can actually put it on an angle and it's true as well. Okay? Whatever the slope is that happens between the endpoints, there's going to be a matching location where there's a slope that's doing the same thing. Okay, that's all it's really saying. So you can imagine the reason why Rolle's theorem is really just a special case of the mean value theorem is because it actually is true too, right? If I didn't have that condition about being the endpoints the same, notice when the endpoints are the same, what's the slope of that line that connects them? 0. And that's the slope of the line I'm finding up here. Okay? So what we're going to do then is we're going to do this particular set of objectives, right, like the conditions that we're going to check. And then we're going to do the other piece, which is to find the derivative when a mean value theorem exists. So the give and the take that I mentioned before. We only have to check 2 conditions for mean value theorem to apply. We have to check that it's continuous. We have to check that it's differentiable. So there's only 2 conditions to check. But the take, right, the part that ends up being a little bit more work, is that we have to calculate that slope that we're setting it equal to now instead of setting it equal to 0. So don't know that it's any more work. It's just slightly different work to do this particular application. So here's our function. Again, you can see we're using very nice, clean, easy functions. And we're checking first for what? Yep, continuous. So is it continuous?
Yes.
Oh, yes. Why? Yeah, because it's a polynomial. And by the way, that's working because we did work to prove it before. We didn't really just get it for free. We just get it for free now from earlier work, okay? Is it differentiable?
Yes.
Yes. Why? Yep, because it's a polynomial. Okay, so what does that mean? Well, it means the mean value theorem, which we'll abbreviate MVT, like we did the IVT for the intermediate value theorem. The mean value theorem applies. Okay, so we get to the point of deciding whether things apply quicker when we do the mean value theorem. But the mean value theorem says that I have to do this with it, right? I have to find that slope in order for this to work. So I have to find that slope with these ordered pair points. But you can do that. That's an algebra concept, right? You just need to find slope. Now, unfortunately, you only have the x values, right? This is an x1 and this is x2, or this is a and b if you wish, based on the way they've described it, I suppose. So you have 2 x values. That's going to go on the bottom. So as we're finding our slope, I'll even write it out that we're finding slope. We're finding slope, and I'm going to put 1 minus negative 2. If you want to do it the other way, that's fine. But I need to plug the number 1 into this equation, which would give me 1. So 1 squared is 1. I'll write it down in a minute. And then I need to plug negative 2 into that equation. Negative 2 squared is 4. Yeah, so I have 1 minus 4 on top, and I have what on bottom? Yep, 1 plus 2, which is 3. So this ends up giving me negative 3 over 3, or a slope of negative 1. Okay, so that's actually, when I take my derivative here in a minute, what I'm going to set my derivative equal to in the mean value theorem. I'm setting it equal to a slope that usually wouldn't be 0 at this point. So my derivative of x squared is 2x, and we set it equal to that slope, which is negative 1, and we're going to solve it, right? So what does my x equal? Negative 1/2. And again, we do want to make sure that as we're giving that answer that it really is on our interval. It should be, right? We're guaranteed there is one, and it is, in fact, on that interval, right? So there is a c value, and it is equal to negative 1/2. Guaranteed to have a c value by the mean value theorem, and it is equal to negative 1/2. All right, I think we have one more. Yep. Okay, a little bit of a less familiar graph this time. Whoops. Oops, here it is. We have 5 minus 4 over x. So our first question is it continuous?
No.
Okay, and so why is it not continuous? Okay, so at x equals 0, there is an asymptote, actually. Yeah, asymptote, because the denominator is equal to 0 without being able to reduce. It's also true that it's not differentiable because of that. It fails right there, so the mean value theorem doesn't apply. But before you go packing up just yet, I want to change something. Jaden's already got his stuff filled out. I want to change something because the reason this failed was because the x equals 0 was between the endpoints I was given, correct?
Yes.
That's my problem. The problem is not just that there's an asymptote, but that the asymptote's between my endpoints. So what if that were different? What if we had the interval instead of negative 1, 4, it was 1, 4?
Yes, it would be continuous.
It would be continuous, right? That's the one we're actually going to do. So is it continuous? Yeah. And it's continuous because the only domain, we'll call it an issue, is an asymptote at x equals 0, but that's not in my interval. It is a long explanation. I won't make you write it again. So differentiable actually follows by the same reasoning. And we actually had a differentiable statement about rational functions when we talked about this before. And basically they said that if the function is continuous, and it's continuous on its domain, which this is. The domain that we're looking at here is 1 to 4. So if it's continuous on the 1 to 4 and it's a rational function, then it's also going to be differentiable on there. So we get this one for free. So this is differentiable because of the same reason, but it's really because it's a rational function. On its domain. Namely, the domain, of course, here is everything but 0, right? That's what the domain is for this particular function, everything but 0. So this works. So now we're going to try the mean value theorem with this on this interval. So the mean value theorem works. Over here, we did never write it down, I don't think. The mean value theorem fails. I don't think I even wrote it. You're right. I did not. Mean value theorem fails here because it was not continuous. But over here it works. So we do the slope part, right? We have our interval from 1 to 4. So we find f of, I'll do it this way, and left to right this time. I did it from right to left last time. So on the bottom I have negative 3. So what is f of 1 in this function? I didn't rewrite it. I'm so sorry. 5 minus 4x. Did I write it wrong? Oh, did I write? Hang on. 5 minus 4 over x. I've just put it in. It doesn't matter. This can be written like this, or it can be written like this. It's exactly the same thing when you flip them. So whatever order you want to do them in will work just fine. I just was choosing to do it in the other order this time to show that. But if you want to try it in that order, Callie, that would be great, and then we'll check and make sure that it worked out. So what is f of 1? If I plug the number 1 into 5 minus 4 over 1, I get 1. And what happens if I plug the number 4 into 5 minus 4 over 4? I get 4. So on this one, I end up getting negative 3 over negative 3. Callie, yours should say 3 over 3. Did it? Good. And so I get a slope of 1. I promise the slopes are not always nice and beautiful ones and negative ones. They can be ugly. But you're going to get a slope. So we're going to take our derivative, which is maybe not the nicest thing that we've ever done. So I need the derivative of 5 minus 4 over x. So what's the derivative of 5?
0.
0. That's good news. How about the derivative of the negative 4 over x?
Negative 4
It's 4 over x squared.
Okay, so one of the ways to change it is to rewrite that part of it as negative 4x to the negative 1, right? So if I take the derivative, what will I get?
Positive 4 over x squared.
Yep. After I do the derivative and then I simplify, I would get positive 4 over x squared. And I'm supposed to be able to set it equal to that slope that I just calculated, which is the number 1 on this one. So you can cross multiply, right? So this 1 is the same as 1 over 1. So if we cross multiply, I actually get x squared is equal to 4. Now technically x is equal to what?
Positive and negative 2.
Positive and negative 2. But c is not equal to positive and negative 2.
It's only equal to positive 2.
C is only equal to positive 2. How come?
Because intervals.
Yeah, you got to go back and make sure that you're looking at the interval you're talking about. It was guaranteed to have at least 1, and it could have 2. But you have to make sure you're on the interval. So I do have 2 possible values. The only one that's on my interval is c equal to 2. Any questions? Awesome.